This is a nice article that, oops, what did I do with the PowerPoint? There it is. That looks at how we can make AI more efficient, more economical. We talked about the impact of AI on energy consumption, water consumption, and how we have to worry about AI being sustainable now because it's become quite ubiquitous. It's everywhere and it's trying to do everything. In our business climate, of course, we are hoping to combine big models with monstrous high performance computing, merge them with AI to improve the models, to make forecasts, and so on and so forth. So this is an article that says cutting AI down to size, a $14 chip incorporating tinyML AI models, actual size shown. Okay, this just appeared a few weeks up, actually literally last week. Um, What's the point of the article? The small drone circles the cashew tree, its rotor arms spray out from its compact body like a water strider's. As it rises, its camera captures a bird's eye view of the foliage, which shades from a dark glossy green at the tree's bottom to a purplish green at the top. Meanwhile, an artificial intelligence model built into the drone determines whether the leaves are diseased, based on telltale black or brown splotches, or healthy. If needed, the system can one day direct other drones toward individual sick plants to treat their disease with a spritz of pesticides. So it's just going around individually catching diseased leaves and trying to fix them. This system is a handiwork of Bala Murugan, the computer scientist at Vellore Institute of Technology in Chennai, India. Murugan comes from a family of cashew farmers, including his father and uncle. They apply a lot of pesticides on the cashew. He says, I wanted to build a solution to minimize the application of pesticides. A fantastic goal, right? Good aim, good health relevant way of doing things, but he needed a solution that can't require internet connectivity, which is often hard to come by in rural India. Murugan drew on his technical expertise. During his PhD, he had worked on small, cheap processors. Now he realized the AI models running on such small devices could help farmers like those in his family quickly identify and treat cashew disease. That's when I ended up using tinyML, he said. One word, tinyML, name of model. tinyML, the ML stands for machine learning. Of course, is a low-cost, low-power implementation of AI that is being increasingly adopted in resource-poor regions, especially in the global south. In contrast to the large language models that have dominated the news with their versatility and uncanny knack for human-like expansion, tinyML devices currently have modest specialized capabilities, yet they can be transformative. Murugan's tinyML equipped drones, for example, have been able to identify cashew leaves with the fungal disease anthracnose with 95% to 99% accuracy. They should save farmers time they would otherwise spend looking for signs of the disease by themselves, and their ability to target treatments of diseased plants removes the need to indiscriminately spray pesticides on all the plants, which is both expensive and damaging to health and the environment. So if they see that their orchard or tiny cashew plantation has been hit with the disease, at one point they will assume that it's a problem, so they will prefer to spray the entire plantation and not just individual plants, because it's very difficult to do that. Murugan is one of the many researchers in the global south finding use of tinyML. The devices can serve as low-cost aids for teaching AI skills, but they are also providing homegrown solutions to problems that are not being sufficiently addressed by tech companies like in the global north, from detecting plant diseases to tracking wildlife. About 15 million tinyML devices were shipped in 2020, and that number, according to one estimate, could grow to 2.5 billion by 2030. part of the appeal for Murugan and others is that once the AI model is trained on a personal computer, it can often run for weeks on low power tinyML devices, powered by everyday batteries, sipping as little electricity as a typical laser pointer, okay? And the devices don't need internet connectivity, which can be scarce in resource-poor regions of the world looking to embrace AI solutions. Despite its limited capabilities, I think tinyML, is the future, says Marcelo Jose Rovai, a data scientist at the Federal University of Itaúba, Unifi, I think that's Brazil. It's fantastic for developing countries, obviously. So I'll read all the text. Usually that's not how I would do it, but this is such a nice little paper or research feature that I really want to read it to you. In AI, the trend has been the bigger the better, says Thomas Basicolo, program officer in the Telecommunications Standardization Policy Department of the UN's International Telecommunication Union. The trend has culminated in current state-of-the-art generative AI models, those including LLMs such as ChatGPT that create new content. But the rise of these models has so many issues, Basicolo says, obviously. As LLMs are fed more and more training data and the parameters to fine-tune and expand their ability to answer queries, the models have also grown dramatically in cost. The latest AI hardware chips can cost about $40,000 each, and ChatGPT alone uses tens of thousands of such chips. Okay, here is a little blurb. Small but mighty. Tiny machine learning, tinyML devices are orders of magnitude cheaper and less power hungry than the chips used to run artificial intelligence like large language models. tinyML $2 to $60 cost per device, including sensors, less than 1 to 100 milliwatts average power consumption per device, whereas large language models use $25,000 to $70,000 average cost per AI chip, requiring tens of thousands of chips for a model, and 700 to 1200 watts average power consumption per chip. So generative AI models are also hungry for power, which means more water storage, greenhouse gas emissions, and so on. Some estimates have ChatGPT sucking up almost 600 megawatt hours of energy every day, more than 50 times what an average US household consumes in a whole year. And it took considerably more energy than that to initially train ChatGPT with massive amounts of data. That's why it sounds so smart now. These models typically run remotely on huge data centers accessed through the internet or in the cloud, which means users need internet connectivity. The estimated tens of billions of liters of potable water needed every year to cool data centers leave a profound environmental impact. We have discussed this elsewhere, especially in areas where drinking water is already scarce. Every time that you ask ChatGPT a question, several liters of water are used cooling the big machines that are running big data centers in the cloud, Rovai said. Okay, so things we do that we don't even think about, and they cost. We have talked about the carbon cost of email, spams, cup of coffee and bananas and so on and so forth. So now we are saying AI can do everything, and now we are going back and saying, well, is there a better way to do it than to run these monstrous models? Of course, it's not either or. It's about minimizing big models in favor of small models in places where resources are limited and the task can be done with tinyML, right? In 2019, former Google engineer Pete Warden explored a far less resource-intensive approach. He and his colleagues pared down traditional machine learning models by tweaking the numerical values that define how a model learns. They could cut unnecessary values and also reduce the precision of others without losing much overall accuracy. Result, models that could run on computer chips with limited memory and processing power. tinyML models now rely on microcontroller chips similar to those found on everything from washing machines to car airbags. Warden and others first envisioned tinyML consuming so little power less than 1 milliwatt, that devices could run for a year or more on coin cell batteries and virtually forever using solar power. There's some magic stuff that happens once you get below 1 milliwatt. One says they haven't reached that threshold widely yet, but tinyML devices can run for weeks or sometimes months on AA batteries. Just think about this, okay? You are in a village, poor farmer, and you're having a farm, and you're trying to optimize everything without investing too much, and there is this magical device that can do so much work for you. The chips themselves are cheap and commercially available from several different manufacturers. As a result, most tinyML devices now cost from a few dollars to tens of dollars, depending on how powerful they are. They often include not just the chip, but also cameras and sensors to detect images and sounds for the AI models to interpret. Much of the software, hardware, and data sets that researchers need to get started with tinyML are open source, which means they can freely access and modify them. tinyML models typically use less data than larger varieties, ingesting thousands of images or sounds instead of millions that LLMs often require. LLM is trying to cater to a very wide audience with various interests, and they can ask any question, whereas tinyML will be typically running a particular task, like monitoring leaves of cashew plantation, leaves of trees in a cashew plantation. Murugan, for instance, says he used 20,000 images of cashew anthracnose disease collected from various public domain sources to train his model, although he's supplementing the data set with his own photos to improve the model's accuracy, make it local specific. Once trained, the model does all its computation on the device, so tinyML systems can provide results within milliseconds with no need to go to the cloud and back. With no need to connect to the internet, tinyML uses less power and also tends to be a boon for the privacy and security. It's a boon for privacy and security because you're running off the net and not putting your footprint all over the internet with what you are doing. Okay, obviously there will be other concerns with that, but nonetheless, here is an image. An artificial intelligence model running on tinyML learning devices is helping clean up efforts in Malaysia quickly classify types of trash hampering the growth of mangroves, including plastic food containers, plastic bags, food wrappers, etc. that you see here. That's been mapped, just this tiny drone flying around. Yoao Yamashita first came across tinyML in 2020 while completing his undergraduate degree remotely because of the COVID-19 pandemic. An electronics engineer at Unifei, Yamashita spent this time at his home in Mogiana Paulista, coffee growing region in the southeastern part of Brazil. Yamashita realized that many small farmers were struggling to diagnose diseases in their coffee plants. Specialists to do this diagnosis didn't come cheap and wouldn't travel during the pandemic, so Yamashita turned to tinyML for a possible solution. After using public datasets to train a generic AI model, Yamashita went to the farmers to find out about coffee diseases specific to Brazil. At first they were very skeptical, he said. A lot of them don't even have cell phones, so an AI model to auto-detect disease was very, very new, he said, and they're obviously skeptical. To fine-tune his model, which runs on tinyML devices about the size of a pack of cards, Yamashita took photos of healthy and diseased coffee leaves from rows of coffee plants growing on hillside plantations in his home region. He also collected samples and photographed them later under more controlled light and background conditions. The resulting models could identify a variety of coffee diseases with 96% to 98% accuracy, including fungal diseases such as foma, sooty mold, and rust, as well as the leaf miner moth. A farmer could point the device's camera at a leaf, and its screen would show the disease name and a score indicating the model's confidence. When I showed the farmers the device working, they looked like they were amazed, says Yamashita, who is now working on tinyML devices for other users. So, proof is in the pudding. So he just flew the thing, showed them the results, and they were like, "Whoa, The device is practical for poor farmers. Yamashita says it doesn't need internet access, lasts a week or more without needing to charge its battery, and costs less than $20. It's just the sort of bespoke, homegrown solution tinyML is good for, and explains why agriculture has been a popular use for the technology. Beyond agriculture, researchers are also developing tinyML devices for healthcare applications, from detecting arterial fibrillation, a type of abnormal heart rhythm in Brazil, to anemia in Peru. And multiple groups have used the technology to distinguish mosquito species by the buzzing of their wings, making it unnecessary to collect mosquitoes in traps and manually identify each one. The result is speedier alerts that could help with control of species that spread disease. Okay, yeah, maybe it's a little too much, so let's try to skip some of the text. I'm excited to read this to you, because when I read it I thought this is a really nice story, but once you start reading it you realize that it's a little too much. Okay, so Rawai gives other example using AI model to identify species of Aedes mosquitoes and so on. Being able to categorize that mosquitoes thing in with carry malaria in an automatic way is a huge advantage for people working in the field, obviously. And this is people who are from the ICTP in Abdus Salam International Center in Trieste, Italy. Similar devices are also finding their way into environmental applications, which obviously is our main goal. And there are people who plan to make some of the environmental data publicly accessible to help track the location, quantity, and types of plastic waste. The example we just looked at here, plastic waste is a menace. We want to deal with it. This will help not only those who pick up the trash, but also local council and environmental agencies to further plan their waste collection activities. Okay, so obviously they are going to expand that further as well. They are also doing water quality work in lakes using the same technique, and other tinyML researchers are trying to use the same system to send data from tinyML devices used in agriculture to farmers' computers or phones. So imagine having a handheld device which is getting data from the drones flying around in your farms, and you can take action. So without a way to download the data remotely, the farmer will have to go through all these devices. It's time consuming and it's tedious. So obviously developing tinyML devices that can detect diseases in cotton and reduce the need for pesticide use is going to be making farmers very happy if that can be implemented. So simple as tinyML devices appear, as simple as tinyML devices appear, developing them can be a challenge, so there is always a catch. For one, it requires expertise in multiple skill sets. It's combining hardware, software, and machine learning. Very few people can do all of these, so combining all these skills also takes time. But imagine that you are on a technology campus like the Indian Institute of Technology in Bombay, where I'm recording these, and you get kids to build these things and fly them around the campus to identify trash spots, because the campus has decided to go plastic free, even though plenty of it is floating around. They are trying to do sustainability, net zero, and so on, but this kind of a device can be an excellent learning lab project for the kids as well. So there are kits being developed which have been used to train students at the universities in Malaysia, Saudi Arabia, and elsewhere. In just an hour or two, students were able to train tinyML devices to recognize words and phrases in their own local languages, which is empowering for communities. Okay, so limited capability, of course, because these are small devices. A tinyML is very good at any problems Yamashita says that we talked about. Microcontrollers that run the devices have extremely limited memory and computing power, which makes them more suited for highly specific tasks than generalizable commercial products. So the example of a campus monitoring for things, water quality, or for tracking trash, and so on, is a very specific task and easily done as a project-based learning team building, etc. So device could be great at identifying words in the language or identifying diseases of one plant species, but it's less likely to serve as a universal translator or identify diseases across all plants. And this issue is important also at learning institutions, because often learning is done in English in science after 12th grade, but many kids don't have the required level of expertise in English. Maybe tinyML devices can help them in their particular language. They don't need a LLM, for example. Yet, the appeal of smaller models that run directly on devices is dawning on many tech companies in the global north, including Apple and Microsoft. Obviously, they will always be after anything that can make them money. For some applications, such as taking an order at McDonald's, specialized tinyML models that can run on local devices rather than in the cloud at lower cost and power use may be preferable to running an expensive general LLM. Sometimes these large language models are doing way more things, way more than you might need. Okay. Meanwhile, tinyML devices themselves are rapidly becoming more powerful. Just a few years ago, it was considered ridiculous than relying solely on data centers. Yeah, okay. At the same time, the simplest tinyML devices are likely to become more prevalent as microcontrollers continue to become cheaper and more powerful, with some already being developed specifically to run AI. As Mashita puts it, tinyML will enable AI to in fact go everywhere, because there are other peoples looking at the maturity point where we are now, seeing solutions and technology that can be commercialized is not free, and there are people running free massively online course on tinyML and has written an open source book about it. And even though each tinyML device may be relatively small and specialized, many such devices talking to each other could help tackle bigger and more complex tasks. So here is example. Tiny machine learning projects around the world aim to tackle challenges in the global south, including identifying diseases such as rust in coffee leaves in Brazil, that's here, tinyML devices to detect mosquitoes in the field here, and that already mentioned, heart disease rate and other physiological readings are also being developed in workshops. So here is a student, looks like, has built something and is testing it out, and this is really going to be exciting for the global south if it can scale up and do many things without so much power, without internet, without cloud dependence, and so on. Okay, so let's leave it here. It's a nice topic and very current, so I wanted to include it here. Okay, see you in the next topic.